Hey students, thought I'd make another video solution. Got a question here about this number 50 here. So let's give this one a little bit of try here. I'll read it first. It says a kangaroo can jump over an object 2.5 meters high. Okay, then the questions begin. Calculate the vertical speed when it leaves the ground, and then B, how long is it in the air? Now, I just want to take a moment to remind you of these 5 useful equations, and really they're kind of derived from each other, so you can decide to memorize either none of them and derive like this one by doing an integral and then an integral again. Probably best not to do that. Probably best to at least memorize these 2, because then you could get the other ones from this. For example, you could solve this one for acceleration and put it into here, and you get this equation. Or let's see, you could solve it for time and put it into here. No, excuse me, solve for acceleration and put it into here, and then you would get an equation without acceleration. And you'd get this. So I did that on some other videos. The one I always do the least, and I got to think about this, is solving this one for initial velocity and putting it into here. And then you get an equation that has final velocity instead of initial velocity. And it turns out that instead of a plus sign, you get a minus sign. But what's nice about these 5 equations is, and let me pause. Keep in mind they only work for constant acceleration problems, okay? So don't ever use it if it's non-constant acceleration. Or if it's one like that number 40, that harder one with Usain Bolt, where we do have one problem that's divided into 2 pieces, where they have like the first 3 seconds of Usain Bolt has a constant acceleration, and then after that, the rest of the race, and then there's 2 parts to it, a 100-meter race and a 200-meter race, there is a constant speed, so that's 0 acceleration. So what you can do is you could apply these equations twice. You could kind of break the problem into 2 pieces. So that's one way of using these equations. Even though the whole problem doesn't have constant acceleration, you still might get away with it if parts of the problem have constant acceleration. And so you can say like there's part 1, and then the ending parts of 1 become the beginning parts of 2, okay? Now, in this problem, though, what I want to emphasize here is that, like most problems, write down, the 5 unknowns here. And usually, looking at these, of course, remember you can only use them for constant acceleration. So they either have to say what that acceleration is or give you some kind of indication that it's a constant. They may not tell you what it is and ask you to solve for it like they do in the Usain Bolt problem number 40. But in this case, since it's jumping, we know it has to do with gravity. So we know it is a constant negative 9.8 meters per second. So that is one of the unknowns, and we know that it has that same constant acceleration as the kangaroo, is jumping up and even on the way down. So on the way up, the acceleration is down and the motion is up, so that slows the kangaroo down. And then as the kangaroo comes down, again, the acceleration is still down, and then the movement is down, so that speeds it up. But you always have that negative 9.8. So we can apply this for the whole problem. We don't have to like break it into going up and coming down. The acceleration is always a negative 9.8, even though the direction of motion changes. It goes positive and then negative. But that's not the condition of these equations. The condition of these equations are they have to have constant acceleration. So we do have that. So this problem is actually much easier than number 40 because of that. Now, it says how high does it, it says how high. So on its way up, we know that it has gained a height of 2.5 meters. So we know that. And actually, that's the only number that is given straight to us. We've got to infer this one. And also, we have to infer this one. It gets to its highest point, and so it comes to a stop. And so you jump up to its highest point, 0, and comes down. So again, they are giving you final velocity, at least, you know, the first half, because that's what A is, calculate the initial velocity. So B is, you know, how long is it in the air? Let's have a longer talk on that. But my point is, they've given us 3 of the 5, and that's kind of normal. That a problem like this, they'll give you 3 of the 5, and there'll be one that they're asking for. So I'll circle it. So they're asking for this one, calculate the vertical speed when it leaves the ground. And that one other variable is not being asked for, and it's not being given. And because of that, that will decide which of these 5 equations to use. You would want to use the equation that doesn't have time in it because you don't know what it is and you're not trying to solve for it. If you were trying to solve for it, you would want it in your equation. Or if you were given it, you would want to have an equation that has time in it so you can use some of the information that's given. They don't usually give you extra information in these problems. So, you know, if time is given, then, you know, make sure you use an equation with time in it. Or if they're asked for time, make sure you use one. But if it's not given and not asked for, find that equation, which in this case is right there, number 3. Number 3 does not have time in it. And so I like to make a little chart here. What is missing? And so time is missing. So I think the key to this problem is actually going to be this one, at least for A. Because again, A does not have time and doesn't ask for it. Now B is a little different because they are asking for time. So we'll talk about that one in a second. But for A, I would pick this equation. In fact, just, you know, kind of as a review, I've noticed that this one is missing distance traveled. This one is missing final velocity. This one is missing time. This one is missing acceleration. And this one is missing initial velocity. So as I go through this list and think about what I have and what I'm looking for and find out the one that is completely missing, that kind of decides where to go. So at least for part A, so that's what I'll do here. I'll say, okay, for part A, let's use this equation. Let's use final speed equals initial speed squared plus 2 times the acceleration times the distance traveled. And then put in what we know. So we know the final speed is 0 for, you know, going up. So again, just looking at A, calculate the vertical speed when it leaves the ground. The initial speed is what we will be hunting for. The acceleration is a negative 9.8, and the distance traveled is a, and I'll even put a positive 2.5, because it goes upward, which is actually perfect, because by the time I multiply these out, I will get a negative number, and then I will move it to the other side. So if I take this 2, and I'll go ahead and do the negative 9.8, and then 2.5, and that's a negative 49. And then when I move it to the other side, it becomes a positive 49. Ah, that was nice. So then when I take the square root, I just get 7. And so 7 meters per second would be the answer here to A. And I guess to follow along with significant figures, I had 2 here, 2 here. Actually, it was 2.0, so I have 3 there. And it's actually 9.80 or 1, depending on where you are on the surface of the Earth. But that's 3. So maybe I should be a little careful and have 3 significant figures for my final answer. So there's A. Now, going on to B, I'm going to kind of do the same thought process. And let me kind of maybe change colors here in my markers. And so maybe I'll just kind of put a box around this information. And I want to emphasize, even though we're going up and coming down, it always has this same acceleration. So for part B, I can still say I have constant acceleration. That means I can use this equation for the whole motion. And it's still negative 9.8. And so I don't have to break it into 2 pieces like going up and coming down. And sometimes I get students doing that, and they don't have to. You can, because, if you break it into two pieces, each piece has this acceleration. And so you have a part 1 going up and a part 2 coming down. And maybe if you've already just done a problem like that, like Usain Bolt one, maybe you're tempted to do that. But remember, the condition of using these equations is constant acceleration, not constant direction of velocity. So that's important here. All right. So again, for part B, I would say that's still true. Now, here's where it gets a little different. Here's where I'm going to change it. For part B, how long is it in the air? We're looking for time. So the one I need to circle is here. We're looking for time. And technically, then, we already know what the initial speed is jumping up. That's what we just solved in A. So let me put, again, in green here. How does green show up on the camera? I hope it shows up okay. It's a little light here. Maybe I should have gone with red. But we know that initial speed. So we're looking for this one. We got that one. Now, I guess I already said about the acceleration. Here's also different. We know that the change in position is 0. It goes up and comes back down. What we don't know is now the speed, because as the speed comes down right before it hits the ground, it has some speed. So this is the unknown one. Although I suppose we could make some kind of argument about what it is based upon A. But I'm just going to go with the idea we don't know what it is. But if it slowed down from 7, then it'd have to speed up for 7. So technically we also know this one is minus 7. Which actually should make part B pretty easy, because that means we can use any of these equations now, because we know everything. But to follow my theme, I'm going to go with the idea that we don't know what the final speed is. And I'm going to come up here and say which equation is missing final speed. It's equation number 2. And so jumping over to B here, I will say x minus x naught is equal to initial speed times time plus 1/2 at squared. And that one, again, does not have final speed in. And I am looking for time. And I know acceleration, distance traveled, and initial velocity. So let's look at the distance. And I shouldn't say distance travel. I should say position change, because it's final minus initial. And if you get back where you started, that would be 0. So that number is 0. The initial speed we said is 7. T we don't know. That's what we're looking for. And the acceleration is at negative 9.8. So go ahead and let me do the negative 9.8 with the 1/2. And so now we've got some math to solve. And if it's been a while since you've done this math, let me remind you, here's a little trick. If you can factor something that equals 0 into 2 factors, it's nice, because the only way 2 factors can equal 0 is either if the first term factor is 0, or if the second factor is equal to 0. Now, the first one's pretty easy to solve. Time is equal to 0, so that's okay. Here, I'll do something like this. I'll move the negative 4.9 to the other side. Then I will also divide. So 7 divided by 4.9. And it looks like 1.43. 1.43. So this one's going to take a little more thought, because we've got 2 options. Either it's 0 time or 1.43 seconds. Now, just to talk about this, you can see why now there's 2 answers. We just solved an equation that said, when does the position change equal 0? And the first answer is at time equal to 0. Yes, right as the kangaroo is jumping, it has a position of 0. Exactly. And so that's right as it's leaving the ground. Of course it's at position 0 at time equal to 0. So that is true, and that's why it comes out to be in our mathematical solution. But it's not the one we're interested in. We're interested in the one that is later in time, after the kangaroo jumps. And so that would be this one. And so the correct answer would be 1.43 seconds before it returns back to its starting point. All right. Hope that helped you. Take care.